All right. So Z-scores is what we're going to talk about today. So how unusual is a value? We've learned how to describe data using the mean, standard deviation, and now we want to answer a new question, which is where does the specific value fall compared to the rest of the data? Um, Once again, everything that we do in this unit is kind of to show you. We'll come back to the heights example because that's what you are going to be doing. Um, where do you fall with respect to the heights of your peers and things like that? So we're looking kind of like at this. Here's a normal distribution bar. We've got this point on here. This is just kind of uh, that symbol right there. That's called mu for the mean. You might see that, but where does this value fall compared to the rest of the data? And that's kind of what we're going to look at today. So there is something called the empirical rule that we're not going to touch on um, a whole lot today, but it's just kind of a quick rule to kind of maybe answer some of this a little bit. But it's broken off like this. When you have one and two, three standard deviations, um, it says that 68% of all observed data will fall within three standard deviations of the mean or average, and and so 68% of the data will fall within one standard deviation. That's including above and below this little green area marked, and then. If that's the case, and that should make sense, right? That's a pretty good. We've got this pretty good curve. Think about that in terms of proportion. And then if we go out all the way to two standard deviations, that's going from the left side of that weird purpley pink color all the way to the right side, including the green side in the middle. And that is a pretty good proportion of this curve that would be shaded. So that's going to give us 95%. And we do need to understand, well, I don't want to jump ahead of myself. I think I say this later. I mean, if I go three standard deviations above and below, that we can go further than that. Right now, it looks like it's like ending. It looks like there's nothing shaded, but we can still have things on the far left and right. They're not worth mentioning a whole lot because they're so rare. But uh, in terms of the whole population, we would say 99.7% of all data values that we observe are going to fall within three standard deviations of the mean. Within meaning inside of this bell. Rahab. So, but what if it's not exactly one, two, or three standard deviations? Um, sometimes, we need to look at other values and figure out where exactly we're going to fall. So, many values fall between standard deviations, not exactly on the mark. So, how do we describe precisely where the value falls? And that's where scores come in. So, a Z score tells us how many standard deviations. It's not like one, two, or three standard deviations. It tells us how many standard deviations. So when we label these, we're labeling even one, two, and three above and below, but we could have a standard deviation like you would say a z-score, like if you get a z-score of 1.67, that would be, I don't know why I said 0.67, let's say 1.34. We know that that data value is going to be in between one and two standard deviations, closer to one, but we can clearly kind of mark it and see where we compare with the rest of the population. So it describes the location of a value within a distribution. So just to kind of visualize that for a second, consider the normal distribution for BMI of men in their 60s. A man has a BMI of 30, which we're told is less than one standard deviation above the mean. So if this is our graph to represent that, if the mean is 29, 35 would represent one standard deviation, and we're told he has a BMI of 30, which is less than one standard deviation. We don't know how much less. We just know it's less than one standard deviation um, above the mean. So, and then we would say if there's 29 as the mean, where would 30 fall? Well, this looks like how these are scaled. 30 would fall kind of close to 29, right? It's the next number in the sequence. And so we can label it accordingly like that. Is this value above or below average? Well, 30 is above average because it's above 29. It's larger than 29. Is it close or far away from the mean? It's very close to the mean. It's the next number away from the mean. Would the z-score be positive or negative? We haven't talked about that yet. but the z-score here would be positive. We are on the right side, the above the mean, so it's going to be positive. We'll talk about in a second when we have negatives. Would it be close? Would it be closer to 0 or 1 in terms of uh, in terms of the z-score? We haven't talked about how to calculate that, but the closer, I'm kind of getting ahead of myself with this. So how do we measure exactly how far from the mean? We use this formula. So the z-score is just equal to a data point. So in that BMI thing, 30 would be the data point minus the mean divided by the standard deviation. That's going to give us how many standard deviations above or below the mean we are if it's positive or negative. And we also need to consider that anything above anything more than 3 standard deviations away. So if z is above 3 or less than -3, that is highly unusual. And so sometimes we use those terms to describe our data, like that's an unusual data value. So when we interpret z-scores, we can interpret them in 3 ways. When the z-score is positive, that's telling us that we are above average. If it's negative, we're below average. And if it's close to 0, like my last slide said, that means you're pretty close to average. Looking at the graph, we can see that we are close to average. And so as we go through, a lot of the times I think it's helpful to label our graphs and then label the data value where it fits on the graph, and then kind of have an idea before you calculate your z-score, what's some things that you expect to happen as you go through that. Is your z-score going to be positive or negative based off of the location you already have marked from your drawing? And then also, if we label 1, 2, and 3 standard deviations and you're in between 1 and 2, I would expect my z-score to be something like 1.89 or 1.76 or something like that. So anyways, let's look at this example real quick again. And so I have, do I give you the mean? Oh, it's labeled on here. And I give you the standard deviation of 6. So we're going to see how this formula works. I'm going to predict that for one, and it's not really, I mean, it's a prediction, but it's like I should know this from looking at this graph. First of all, I should expect my z-score to be positive, and I expect it to be less than 1 because 1 standard deviation is 35. I should also expect that number to be pretty small, like close to 0, because it's next to the mean. Okay, so here's what I would do. I'd plug in my data value, 30, minus my mean of 29 divided by 6. And when I hit enter, I get 0.17. And so for one thing, this is positive. This is a small number. This is closer to 0 than it is 1. Remember, 1 standard deviation is the number 35. This is telling us how many standard deviations we are away from the mean. So we are 0.17 standard deviations above the mean, is how we would say that. So this is above average, and it's closer to 0. Let's look at another example involving Jordans. This one's in your notes. The other one wasn't. So if a pair of Jordans costs $247, we're given the mean price is $279 and a standard deviation of 16. Label the mean and 3 standard deviations on the curve. So we're going to start with that real quick. I'm going to put 279 in the middle like I have before. And before I even calculate this, do I have this labeled? Hold on. Hold on. I have these. I needed to see that first. Okay. So, hold on one sec. All right, let me go back to this. I think I changed the order of that. So I needed that to show up. Oh my gosh. Hold on. Okay. Here's my mean and my 3 standard deviation lines. And I'm going to put my mean in the middle, count 16 each time to the right, subtract 16 each time to the left. And then I'm going to, before calculating, $247. Well, that's our data value. That is below average because that is to the left of 279. So that's $247 is below the mean, and it appears to be exactly two standard deviations below the mean. So this is one that it fits like evenly, not like that last example, but it fits evenly. And because 247 is right here, where my mean, two standard deviations below. So because it's below and it's exactly 2, my z-score should be -2 when I calculate that. So if I go and plug this in, I'm going to plug in 247 for x, 279 for x bar, and 16 for standard deviation. And I get the following, -2, which is what I expected to happen because z-score represents how many standard deviations above or below your data value is. So let's say we're given a z-score and we're asked to find the data value. So I'm given how many standard deviations above or below the mean is, and I'm given a data value. Let's put this in perspective too. So first of all, my z-score is 2.19, which means I should be to the right of the mean because that's a positive number, and I should be right above 2 standard deviations when I mark this out. I always want to start by making my sketch. It looks like I don't make my sketch here, which kind of is frustrating to me. But I'm given a distribution with a mean of 60 and a standard deviation of 21. So what I'm asked to find is the value of a z-score of 2.19. So here I'm plugging in the z-score 2.19 for z and not the x like I did the last time. And this is because I'm finding a data value, which is what x represents. I hope I have a graph of this because it's actually a lot better to see this. But we would cross multiply. 1 times x minus 60 is just x minus 60. Then I'd multiply 21 by 2.19 and get 45.99. And then I just have a one-step equation. Add 60 to both sides, and I get x equals 105.99. Here's my graph. It comes up later. Okay, so if this is my graph, here's 60 labeled in the middle for my mean. My standard deviation that I'm counting up 21 on the right and subtracting 21 on the left. Where would 105.99 fall? That would be right about here, right? If that's 102 and the next 3 standard deviations 123, 105.99 would fall slightly above 2. And then if we were to just graph it on there, and then look at our z-score. Our z-score says it's 2.19. Well, with respect to this graph, I mean, it they match up, right? So if I were to not give you the z-score of 2.19 and just give you this graph, I would and ask you what do you think the z-score is? I would say it's something kind of like 2 point something, closer to 2 than 3 because of how close 105 is to 102 compared to 123. Okay, we're going to look at this example involving 2 different groups, the WNBA and the NBA. I'm given different means for their heights, and I'm told the tallest player in the NBA and the WNBA. And I want to compare these across groups. And basically, I'm going to be determining which one of these heights is more unusual. So in the WNBA, we have a mean of 72 inches with a standard deviation of 2 inches. And the tallest WNBA player is 80 inches tall. Meanwhile, the NBA has a mean of 79 inches, so quite a bit taller than the WNBA. The standard deviation is spread out a little more for 3 inches. And then the tallest player is quite a bit taller, 7 inches taller than the tallest WNBA player at 87 inches. So we're going to go and find the z-scores of these. So I'm going to start with the WNBA by taking the 80 inches for my data value minus my mean over my standard deviation of 2, and I get z equals 4. Keep in mind what that represents. That is 4 standard deviations above the mean. We've only done 3 so far. If I do the same thing for here, we would have 87 as our data value minus our mean of 79 divided by 3, and we get 2.67. So which height is more unusual? 80 inches in the WNBA, because this player is 4 standard deviations above the mean. So to visualize the results, here's what we're looking at. So here's the WNBA. Where would 80 inches fall? These are going by 2s. This is way out here where that area is like almost completely flat, right? So that's way more unusual than when we look at the NBA. We label everything accordingly, and we put our point. Now, that's still high. I mean, that's still pretty tall, 79 inches. Sorry, not 79 inches. What did we say that was? 87 inches. Okay, that's still pretty tall, and it's still quite a bit away from the mean. But which one is more unusual? Definitely the WNBA player. So we're going to do the same thing with our heights. We're going to use, like in my example, since I'm dealing with heights, yours going to do yours. You're going to collect whatever question you're asking. You're going to, or whatever thing you're measuring, you're going to use your own measurement as well as part of your data selection. So here, I'm going to use my height since my examples have been dealing with height. So I'm going to find my z-score uh, compared to my sample. I'm going to use my height as the data value, the mean, and the standard deviation, and I'm going to calculate my z-score for boys, girls, and both combined. I'm going to label my height on each curve and add it to the spot under the summary statistic group on the Google Sheet. So going back over here, what I want you to start doing with the building part of this and structuring it is we already have a histogram. We're going to move that down, and we already have normal distribution with only standard deviation, and you should have a histogram somewhere over here and over here and over here. But underneath that, we're going to write my height. So, and once again, if you were doing something else like shoe size or speed, my speed, whatever, you would need to record yours as well because you're going to be comparing yourself to your sample, to the population. So I'm going to have my height here, and I already recorded my height in inches. So this is not a formula. This is like I actually have to type in 71 because that's like a data value. And then my z-score. So where do I fit? So here's how I'm going to do this. Remember, it is the data value minus the mean divided by standard deviation. Well, I have a cell that has my data value in it. Up here, I have a cell that has the mean, and right here, I have a cell that has the standard deviation. So I'm going to go through, and I'll zoom in so y'all can see this. So like right here, you see I-19 minus I-3. What is I-19? I-19 is my height minus what is I-3 or I-3 is the mean right here. So I have that in parentheses because I want it to subtract before it divides. Because these things are subtracting. I need to subtract those and then divide those by the standard deviation, which is in I-18, which is right here. And I get this. I get my z-score of 0.291. So what that tells me is, first of all, I'm above average, but not much, right? Because I'm not even one standard deviation above average. I'm closer to zero than I am one standard deviation. So I'm closer to the mean than I am one standard deviation above the mean. So I should be able to kind of sketch that. And if I drew this up, I would have 70.1 in the middle, and I would be adding 3.2 every time. And then my height, my line would be right next to the right of the mean at 71. You're going to do the same thing for once again your height, and I also want you to have your partners because we're going to do in between as well later, so you can have your height, your z-score, and you can go ahead and put your partner's height, or we can wait until tomorrow. We're going to deal with that tomorrow. But you need to calculate your z-score for each one of these groups, and that's just comparing where you sit, how your data value falls compared to the population that you collected in both the boys, girls, and then both combined. So we can see here, with girls, obviously, I'm my z-score is 2.2, so I'm quite a bit taller, which should make sense because, as we hopefully should see by now, and what we probably already aware of, is that guys are taller than girls. Like, I mean, it's not always the case, but in general. Okay. Last thing is we're going to on your project, you're going to write an interpretation of your z-score. You're going to use this structure. You're going to say my height is, or my speed in this is, or my blah 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 is, whatever it is, and your unit of measurement. The mean is blank with a standard deviation of blank. So you're just restating it. And then you're going to say what your z-score is, meaning I am how many standard deviations, and then this should say above or below the average. Guidelines are, I know we said above and below 3 standard deviations. Really, if you're 2 standard deviations or more, like you want your, like a typical range is going to be less than or equal to 2, like in that ballpark. So in the middle of 2 above and 2 below is more of a common range. Yes, you have people that are more than 2 and less than 2. Definitely it gets less and less the closer you get out to 3, but we're going to write something like this. If it's more than 2 or less than 2, if it's in this range, we'll say that that's typical. um, if if my z value is less than -2, I would say I'm unusually short, or if it's greater than 2, I would say I'm unusually tall. And then once again, I've changed the delta math, but you do have delta math. So y'all should be going through and by now started collecting data. So make sure that you're following this kind of template that we're working with, because this thing, like y'all's, needs to look like this with your own data values so far. Um, and and then you're going to transfer some of the information that we find on the poster that you create for your normal distribution.